as the introduction stated, I work on saturated riparian buffer zones, and the work that I'm going to present is actually outside of the Mackinac system, but it's relatively close, and it's a topic that kind of fits in pretty nicely into it and can be transferred to almost anywhere. So I'm working in a saturated riparian buffer zone up near Hudson, Illinois. It's actually a restored prairie, and over in this area we have a field, and then what was once farmed is here. This is what has now been restored. It's part of the Comar Park area, and then there's a stream here that runs. The diversion box, and I'll show another picture later, or the tile that comes into the system comes across here and then is diverted in this direction up north. But the purpose of the saturated riparian buffer zone is ideally to help remove some of the excess nitrate that gets into the drainage. And then so we were interested in this aspect. And what we've found, and so I'll hit the key points and then we'll go through, is we see denitrification and plant uptake happen in this zone. We don't see a buildup over time of nitrate, so we've been out working on this site since 2015, and over that time there has not been a slow or gradual buildup of nitrate, so telling us that it's actually being removed. And then and so in this regard we see that it could be an effective means for nitrate removal. Okay. In terms of the overview, we'll just go through an introduction, some goals, or the study site, the methodology, results and discussion, and then get into some conclusions. So we're in an area that is dominated by soils that aren't the most effective at draining. You're probably aware of this, and then as a result, we've put in a number of tile drains and tile systems to help drain that water more effectively to the streams. If we look at this in combination with fertilizers and fertilizer application, we get a system where we put on a lot of fertilizer, and then that fertilizer can then quickly go into the system. Here's where we're at. The tile system, what we would look like if we didn't have the drainage networks. So we've come in, we've put in the drainage networks to drain the soils. They've been highly effective in terms of allowing for the crops to grow and produce, and this area has become one of the most dominant, in this area, the central Illinois area has become one of the most dominant corn and soybean producers in the world, and so that's the nice outcome. Some of our issues, though, become what happens when excess nutrients get into the streams, get into the waterways, get into the reservoirs, and this is where we start to see algal blooms. And the algal blooms then are an issue because of fish die-offs and fish kill when the blooms start to decompose, and these will move downstream. We'll get into the Gulf of Mexico, and then we look at the dead zone. So this was an impetus for the nutrient reduction strategy and the Gulf of Hypoxia action plan of 2018. And as part of that, we have the goals of reducing nutrient loads, specifically in this case nitrogen, by 45% by 2035, with an intermediate goal of 20% by 2025. And so some of the ways that were introduced or have been suggested as means to reach this goal is through wetlands, cover crops, and saturated riparian buffer zones. And so that's the focus that we've been working with. If you're not familiar with saturated riparian buffer zone, let's see if this okay. Here's the traditional drainage system draining right into the stream. In a saturated riparian buffer zone, the tile system is intercepted. The water then is diverted into the riparian buffer zone adjacent to the stream, and then the water itself moves through the soil into the stream, and it's through this process of moving through the soils that we're hoping to reintroduce the processes, in this case plant activity, denitrification, that will remove and abate some of the nitrate. So this is just kind of a quick schematic to give you an idea of what can occur. We have nitrogen in the soil. That nitrogen in whatever form can go into ammonia, which can go into the nitrites to the nitrates, and then at the nitrate level we can either denitrify this or it can be assimilated into the plants. And this is the goal that we had hoped for with the saturated riparian buffer zone. And when we started this then, we were really interested in asking some basic questions. One, does the tile flow change the nitrogen concentrations in the SRB, so the saturated riparian buffer zone? This would seem like this would be the case. You're introducing water into the zone. Does that nitrate move into the zone and actually increase the concentrations? And if so, then are those concentrations consistent across multiple seasons? Do we see the concentrations remaining the same? Do we see them wax and wane? Is there some type of seasonal trend? If they're being removed, what are the mechanisms that remove the nitrate, and do the nitrates accumulate over time, so from year to year? And all of these four questions then go into the one that's in bold above, is, are these SRBs effective in removing nitrate? We've been out there, as I said, since 2015 working on this, and it has kind of grown as we've grown in terms of the research that's been done. Back in 2015, after the tile system had been installed, so here's the drainage tile that would be going to the stream, here's the diversion box that intercepts it and diverts the water out into the riparian zone. In that, after the first year, we put in a series of wells away from the tile and then across the tile to gain an understanding of what's happening without the influence of the tile and what's happening in the area of the tile. Nearer the tile, we have a series of nested wells. The tile is about roughly a foot to below ground, to a meter below ground, and we put wells in that are 1.5 meters, 1.8 meters, 2.3 meters, and then 3 meters below the ground. So we're trying to get an idea of how much of an influence does it have in the subsystem. Our geology of the area is such that we've got a layer of organic topsoil. We've got weathered materials that can be classified as a clay loam. Under the clay loam, there's an area of a sandy gravel, silt clay loam, going into more of a clay. And then underneath that is a very dense diamicton glacial material that restricts flow going any deeper. And that occurs at a roughly about 2 meters plus or minus a half a meter there. So we're really looking at that top 2 meters of the surface. This is what our nests look like, and then we have some instrumentation depending on the project and what we're doing out there, where we're recording water temperature, the stage, the conductivity. In terms of the projects that we've been doing, we've been collecting water samples out at the site since 2015. This has been ongoing up until around this past year, 2023, into 2024. We've at times classified and grouped the wells as either wells being up gradient from the tile drain, wells being down gradient from the tile drain, wells that are closer to the surface, wells that are a little deeper that are more in the till. There's periods where the tile runs, there's periods where the tile does not run. So we've got a few different classifications that we've looked at in order to better understand what's going on. We've done the geochemical analysis and run statistics on it, and then we've done some interpretation. So one of the first things that we've done is we were interested in looking at the concentrations as a whole associated with the tile flow. So in this graph, you have what was the tile flow, so how much water was coming into the tile and how much was being diverted into the soil system. And this system is pretty efficient in that it captures all of the flow that's being drained from the field to the east, and all of it is redirected into the soil. So none of it is in the end actually getting back to the stream. It's all going into the soil. So this is the tile flow in liters, and then over here we have the nitrogen concentrations. And what we see, we have up gradient wells that are in yellow, the down gradient wells are in green, and as the tile flow increases, we actually see some higher concentrations in the wells down gradient. We've got some, I'll say, wells in the up gradient area that have some higher concentrations that we're still trying to figure out. They're kind of our problem child when it comes to what we're trying to decipher what's going on. But overall, we do see some higher concentrations, but if we run this statistically, there doesn't seem to be a statistical relationship between nitrate and groundwater location. So something's happening in the groundwater as it's moving through, even though it's down gradient of the tile. So looking at some concentrations in the well systems over time now, taking it out a little bit more, not looking so much with flow. This gray box represents the period when the tile is actually flowing. And when it flows, it's intermittent at times, and then it can be constant and continually flowing for a period of time. But the records indicate that late January to early mid-May is when the tile is more than likely flowing. And again, that's going to be weather dependent. When it does flow, the concentrations in the tile are high. Here's the 10 milligram per liter of nitrate as nitrogen, which is the EPA standard, and the tiles have concentrations that are higher than this limit. For reference, we also plot the stream, so you can kind of get a sense of what the concentrations are in the stream. In terms of the wells all have rather consistent concentrations during the period when the tile is running. For some of the down gradient wells, which include, they're not labeled, include 6, 8, 10, and 12, they end up being a little higher during the period when the tile is flowing versus when the tile is not flowing. And when the tile is not flowing, those concentrations go back down. So again, we're seeing the impact of the tile in the down gradient area with concentrations going up, but they're not at the level of what the tile is. So we started to look at trying to understand, well, if our concentrations aren't at the level of what we're seeing in the tile, we have some possible reasons for that. One is we could just be diluting the water. We've got what is actually a small volume of water coming in from the tile into the system compared to what's already in the system, so we could be diluting it. We could be seeing denitrification occur, or we could be seeing plant activity occur. So one of the students decided to start sampling one of the wells near the tile, and he sampled for a year, and he would go out, set up an auto sampler, and collect samples every hour. And what he was looking for, and what he was hypothesizing, was that during the day when the plants are active, we would see a change in the concentration such that the nitrate would actually go down because the plants are pulling out nitrate, and then at night when they're not photosynthesizing, that there would be a rebound in the concentration. And this is similar to what was seen in soybean fields in other studies. And so going out and starting this, the white represent periods where the sun is up, dark are the evening hours and the nighttime hours, and then so we've got a cycle here of day, night, day. And he saw a trend where lower concentrations during the day rise during the night and then go back down during the day. And so he attributed this to plant activity. Secondary study that we worked on, looking at what's happening in the soil. And so we created a plot system where we had no vegetation, or restricted the vegetation from growing, and compare that to an area where the plants were growing. And at the end of the year, the area where the plants were growing had a lower concentration of nitrate in the soil system than the area that didn't have the plants. And part of that was the plants weren't there to pull items out, but what was left of the plants were decaying and contributing back. So we're pretty confident we see a plant uptake signature. Well, we were interested then in understanding how quickly does the water move from the tile system towards the stream, and as it does, what is starting to happen. Because with the study looking at what the soil concentrations, we actually saw an increase in nitrogen right as the growing season was starting. And we were trying to decipher why is nitrate increasing in the soil during a period where the plants aren't really active. And so when the tile was starting to run, that coincides to this period of higher nitrate. And what we did is we did a tracer test where we put in a given amount of a tracer. In this case, we used sodium chloride and then also a dye that we put into the box, and then that flowed with the water into our system. And then we would measure the concentrations of chloride and nitrate in the tile water and in our well waters to get an idea of how much mixing was occurring and how much nitrate was being removed then based on our mixing model. So our model came out with, this is what should be our observed concentration, and this is what was actually measured. Sorry, I'm not seeing this very well with my glasses, but I think that's what we got. And so there were times where our measured concentrations were actually higher than our observed concentrations, and vice versa. And during these periods where we have observed what should be observed, or what are observed are greater than our modeled concentrations, these are periods here where we're actually have more nitrate than what should be in our system. These periods coincide with being early in the tracer test. So as the tile is starting to run, the tile is starting to saturate the soils. And in doing so, what we're inferring is that it's picking up the nitrate that was being produced because of the available nitrogen in the system, the available carbon in the systems, and the microbes that take the available oxygen, nitrogen, and carbon and produce nitrate. So during this period, they're producing nitrate. And then over here, just to kind of give you an idea, this is also the same time, and it's where we have high concentrations of oxygen. But as we move forward and the buffer is becoming saturated, the nitrogen, or the dissolved oxygen concentrations go down. And the result of the resulting effect of the lower dissolved oxygen concentrations is that denitrification can start to occur. And so as we move out into about 35 to 40 days after the test started, and this is about 35 to 40 days after the tile was flowing consistently, our dissolved oxygen concentrations get into a zone where denitrification should be occurring. And that's where we start to see, if we come back over to this graph, we start to see a removal. We start to see more, we start to see lower concentrations actually being measured in the buffer zone than what should be, that are predicted based on our mixing model. So from the tracer test, we can interpret that we're seeing a loss of nitrogen It would appear that it's probably a combination of plant uptake because of what we've seen in the past, but also denitrification. That's moving us in a consistent direction. Another student was interested then in confirming whether or not we're seeing denitrification. And so she was doing work examining the nitrogen isotopes. And the nitrogen isotopes, along with the oxygen isotopes, can give us an idea of what the source is. So what is contributing the nitrogen. And then if it is denitrifying, it will follow a certain pattern because of how the microbes are pulling out the nitrogen. So we see we've got a pool here that would be considered atmospheric nitrogen. We have a pool down here that is soil and fertilizers. And then we've got some septic down here as well. And the upgradient wells, so the wells that are not influenced by the tile, they're coming in from natural infiltration. These have a signature of nitrogen that is coming from the atmosphere. As we move down to the down gradient side, so move past the tile, these waters have signatures that resemble mineralized fertilizers that have then been denitrified. And then we've got some wells that actually show a mixing pattern of both atmospheric and then ones that have been denitrified, which again fits with our model of what's going on in terms of water coming in from the tile, mixing with the groundwater that was there, but we're also seeing the processes then of denitrification occur. So now, seeing that we've got denitrification occurring, going back to what we've seen with the plants, we were worried about, well, if the plants are involved, do they pull up nitrogen, and then as they go through their dormant season, do they break down and then do they release it again? And does this lead then to a slow incremental rise in the amount of nitrogen that's in our system? And so a student went back, started looking at the data starting in 2015 and then moving forward. And part of the aspect of her work was ensuring that there was no tile flow. So we were looking at, in this case, September and November, because we wanted to ensure that we weren't seeing the effects of the tile introducing nitrogen during the period. We wanted to see a period where the system was kind of back to its steady state or equilibrium. There were some years, though, in which the tile saw some flow because of heavy rains, and so that's why they are missing from the graph. But over the period of time, the concentrations in the wells, the well water that we've collected, they haven't changed, or they have not increased very significantly. And so we're pretty comfortable saying that we're not seeing a year-to-year buildup or an accumulation of nitrate occurring in our system. So to kind of summarize this up and go back to those key points that I had earlier, in this system, this SRB that we're working with, we see all of the water that's coming off of the field or coming under the field through the tile is introduced to our SRB. All of the nitrate that's introduced into that then does get removed, and I didn't mention this when we were looking at the tile or the tracer test, but we see removals of up to 95%. So it's removing up to about 95% of the nitrogen that's being introduced, which is what we're hoping for and what we would hope for. We see both a seasonal and diurnal change. So during the seasons when the tile's not running, the concentrations go back down to what they were before the tile started. When the tile is running, we see some diurnal changes associated with plant activity. This all gets us to the point where we believe we see denitrification in plant uptake as the mechanisms for the removal of the nitrate. And then over time, we don't see a buildup. And so we're feeling pretty good about our system. Now, as I'm going to go to one last slide and I'll make some more comments, but I have to acknowledge those that have contributed to this work. Number of students over the years, and they're all listed. I have some colleagues that have worked out there with myself as well, and then also some funding agencies. And one of these is very important because, and I throw a lot of thanks to Rick Thwaite on this. He got us involved in 2015 and asked us if we would be interested in this. And so the city of Bloomington has been a very strong partner in this along that time, both with access to it and then also putting in the initial wells, some of the initial wells. And so this project would not be where it's at if it had not been for the city of Bloomington, as well as some of these other agencies that have helped fund the students.